All right, section 16.9, the divergence theorem. This is the last of the new topics that we will learn in all of high school calculus. We have made it. All right, so the divergence theorem. Let's give a little bit of an explanation. This will not be nearly as long for this particular part as we usually do as far as explanations are concerned. First of all, the divergence theorem, you may also see it listed as what is called Gauss's theorem, and I think it's G-A-U-S-S, and I think it's just an apostrophe afterwards. There's no additional S, I think. Gauss's theorem, and that's because Gauss is the person who came up with this theorem. So the divergence theorem, the idea behind the divergence theorem is it's going to give us a way to find the flux of a specific figure. Now the basic thing is that the figure must be a closed and outwardly oriented figure. So as you can see down here where it says divergence theorem, if S is closed and outwardly oriented surface containing the region E, the biggest thing here is the closed part. It must be something which is completely closed. So one quick example of a closed, one would be very easy, would be a sphere. Oops, let me redraw that. It would be a sphere. Okay, a little bit better. And a sphere is obviously completely closed. And what we would normally have had to do to find the flux of this sphere would be to take the double integral over S, over the surface, of our force vector dotted ds, or dot with our normal vector dA. And what we would get is, the amount of whatever the substance is coming through the force, we would get that coming out of the surface, perpendicular to the surface, in this matter. So again, whatever's happening on the inside, it's whatever is coming through this surface as it comes outward. That would be something that would be that we've done, and we're actually going to go through and we're going to do this again in a more general sense. But doing the double integral of the surface area for one surface is not so bad. The math can get a little bit messy, but it's not too bad. But what if we had a surface that was a cylinder? Okay, that's not going to look like a cylinder. A little bit better. So what if we had this surface which was a cylinder? Now, this surface can be closed as long as we include the top and the bottom, but it doesn't have to be closed, because what we could have is just the outside part of the cylinder. If that's the case, Gauss's theorem technically doesn't work, and I say technically, I'll explain how that is. But basically, for us to be able to do this, not only do we have to include the outside part, but we also have to include the top and then the bottom part, which you can't see, but all the sides have to be included to use Gauss's theorem. If we were going to do this using our 16.8 and Stokes theorem type thing, we would have three surfaces. You'd have the top surface, you'd have the lateral surface, and then you would have the bottom surface. So you would have three surfaces to deal with here. Three surfaces. And then you could have other kind of figures. You could have a cone, some kind of a conical surface, in which case here you would actually have two surfaces, because you would have this top piece and then the lateral outside piece here. And then, of course, what we've already done, and I will try and squeeze this one in over here. No, I'll just put it under here, it doesn't matter. Is you could have the box, in which case you would have six surfaces. And we've seen that this typically isn't extremely difficult to do, but it is time consuming. It's just a pain. So the idea is, doing the surface integrals for all of these things right here is kind of a pain. So doing these things right here is a pain. We've done them. It's not terrible. They do take a lot of time. but they are a pain. What Gauss's theorem says is that if we're going to be able to take this divergence theorem, which is this one right here, we haven't really described it yet, this makes it easy to do. All right, and that's the general idea. We're taking something which is normally a pain to do to find the flux through these surfaces, and we're going to make it much, much easier. Now, we will not do a formal proof of the divergence theorem. What we're going to do is we're going to show that the double integral of f dot ds, or the surface integral, is going to be equivalent to the divergence theorem for all of our different cases here. So what is the divergence theorem? It is quite simply what it says here. It is the triple integral over E, where E is the enclosed region. So E has to be the enclosed region, so the inside of the sphere, the inside of the cylinder, the inside of the cone, the inside of the box, or rectangular cube, or something, a rectangular prism, excuse me, or something like that. Those are the different possibilities. You're going to take the divergence of that over that region. So basically it's telling us what is happening with the flux as it goes through all of the different surfaces all at once. And you take that with respect to the volume, dV, because it's three-dimensional. So just a real quick reminder, the divergence is del, or your partials, dotted with your vector, PQR. And then you just basically get the partial of P plus the partial of Q plus the partial of R. That's your divergence. So let's go ahead and take a look at, we've got 5 examples to do. We're going to do a sphere, a cylinder, a cone, a box, and I can't remember the last one. But we'll get with them. And we are going to verify all of them. Okay, example number 1 says we've got a sphere. We want to let F equal the vector field 3x, 2y, 0 over the sphere. X squared plus y squared plus z squared equals 9. We want to verify the divergence theorem. Verifying the divergence theorem means we're going to show that the flux through the surface can be determined in 2 ways. We're going to show that it can be done using the surface integral, and then we're also going to be show that it can be done using the divergence theorem. So let's go ahead and do our surface integral first. So when we do that, we are going to have to parameterize. So we're going to parameterize our surface. It is a sphere. Remember, we're just talking about the surface, so we'll go in spherical. So x then is going to have to be, let's see, the radius would be 3. So the radius isn't going to change since it's the outside of the sphere, so it's 3 sine phi cosine theta. Y then is going to be 3 sine phi sine theta. And z is going to be 3 cosine phi. So there's r, basically. Okay, so now we're going to have to do the partials. So we're going to have to do the partial of r with respect to theta. Partial of r with respect to theta is going to be negative 3 sine phi sine theta. Partial of y with respect to theta is going to be 3 sine phi cosine theta. And the partial of z with respect to theta is 0. So r sub phi is going to be 3 cosine phi cosine theta, 3 cosine phi sine theta, and then negative 3 sine phi. We're going to have to do the cross product. Alright, so let's do r theta cross r sub phi. Eliminating the I row and I column is going to give us negative 9 sine squared phi, negative 9 sine squared phi cosine theta. Eliminating the j row and column is going to give us, let's see, that's 9 sine squared phi sine theta, but we have to negate it, so it's negative 9 sine squared phi sine theta. because that was minus 0. And then eliminating the k row and column is going to give us, let's see, what is that, negative 9 sine phi cosine phi sine squared theta minus 9 sine phi cosine phi cosine squared theta. Does that look right to everybody? I think so. Double check that real quick. Okay. So the problem here is, and this is correct, the problem here is when I factor this, because we're going to factor that last one here, because remember I do have this negative 9 sine phi cosine phi, and another, technically because of the negative there, negative 9 sine phi cosine phi there, which would just leave us, if we factor all that out, with sine squared cosine squared. The problem is that is negative, and we want our z component to be positive, so that's not outward as it is. So basically it looks like we just did our cross product in the wrong order, but that's okay. It doesn't have to be the correct order, because we can fix it. So all we're going to do when we go to rewrite this is we're going to say r sub phi cross r sub theta, and it's just going to take everything and make it the opposite sign, because it just means the cross product is going in the opposite direction now. The perpendicular vector is going to go the opposite direction. So we're going to have 9 sine squared phi cosine theta, 9 sine squared phi sine theta, and then after factoring this out, and we're going to change the sign, it's going to become 9 sine phi cosine phi. That's going to be our cross product. So now we've got our n. We are going to need to parameterize the force. So let's go ahead and do that. Put that in blue. So our force parameterized, let's see, so it's 3x, so that's going to give me 9 sine phi cosine theta. It's 2y, so that's going to give us 6 sine phi sine theta, and 0, because there is no component for 0, which is really nice. That it will eliminate that last component on our cross. So let's go ahead and set up our double integral. So it's the double integral over, we're going to do this over d of our force dotted with n dA. Okay, so we're going to have our double integral, leave some space to put our bounds in there. The force dotted with n is going to give us, let's see what that's going to be, 81 sine cubed phi cosine squared theta plus, it looks like 54 sine cubed phi sine squared theta. And the last part doesn't give us anything. dA in this case, remember that's the what it's going to take. It's the domain that we're going to have over this surface. So considering that we're going over top of the surface here, we got phi and theta which are changing here. So this is going to be a d phi and d theta. D phi, d theta. It's a sphere, so we know that phi has to go from 0 to pi to cover the whole sphere, and theta has to go from 0 to 2 pi. Alright, so there's one really cool trick here that I'm going to show you, because you might be looking at this thinking, oh man, if those 81s and the 54s were exactly the same, then I could pull out a, the common coefficient with the sine cubed, and then I'd have a cosine squared and a sine squared left over. Well, we can still kind of create that situation, so let's see what we can do here. Still going to have our integrals. I'm going to change that 81 sine cubed cosine squared, however, to be a 27 sine cubed phi cosine squared theta plus 54 sine cubed phi cosine squared theta. And then don't forget we still have a 54 sine cubed phi sine squared theta d phi d theta. So what that's done is that's given me this piece right here, which then I can factor out the 54 sine cubed phi, and that'll leave you with the cosine squared plus sine squared, which is 1. So what we're going to get now is the integral from 0 to 2 pi, integral from 0 to pi of 27 sine cubed phi cosine squared theta plus 54 sine cubed phi. I'm just going to factor this piece and this piece right here. I'm going to factor that out, which leaves you with the cosine squared plus sine squared, but that of course is 1 d phi d theta. And the really nice thing about that is now it's actually going to allow me to factor out the sine cubed phi, which will allow us then to separate these two integrals. So let's go ahead and factor, slide this down here, let's go ahead and factor out the sine cubed phi, which will leave us with 27 cosine squared theta plus 54 sine squared, I'm sorry, just 54. I apologize. Yeah, that looks right. Okay. So then d phi d theta. That's a 2 pi over there. There we go. So let's go ahead and separate. So now we're going to have the integral from 0 to 2 pi. That's the theta part. So we've got 27 cosine squared theta plus 54 d theta times 0 to pi integral of sine cubed. But remember, we're going to have to rewrite sine cubed as sine phi times sine squared, but sine squared is the same as 1 minus cosine squared phi d phi. Alright, on the first one we're going to have to do a reduction. So let's go ahead and reduce. So that's going to be 27 halves times 1 plus cosine of 2 theta, and then plus 54 d theta. And over here we're going to have to do a u substitution. So u here is going to have to be cosine phi. du is going to be negative sine phi. Sine phi d phi. So d phi is going to be du over negative sine phi. And we're going to go ahead and change our bounds at the same time here. Now what you will find here is this is not one of those where it's going to just make everything go to 0, because we're only going from 0 to pi. If it was going from 0 to 2 pi and doing a u substitution of a sine or cosine would make the bound 0. But this is 0 to pi, so we can't just get rid of it. Alright, so changing the bounds, cosine of 0 is 1, cosine of pi is negative 1. We're going to have sine phi 1 minus u squared, and the new d phi is du over negative sine phi. Alright, and I'm going to continue on with this piece right here. The sine phi's are going to go away. The negative I can pull out to the front, but that'll flip the bounds. So now we're going to have from negative 1 to 1, so it looks right, of 1 minus u squared du. That one will be pretty easy for us to go ahead and evaluate. Let's go ahead and simplify the one over here in the red just a little bit. Distributing the 27 halves, we're going to get 27 halves plus 27 halves cosine of 2 theta plus 54 d theta from 0 to 2 pi. Okay, I'm now ready to take antiderivatives in both cases here. So let's go ahead and do that. So we're going to get, let's see, that's going to be 27 halves theta, and yes, I know I could have combined the 27 halves and the 54. I'm just choosing not to right now. Plus the antiderivative of cosine is sine, 2 theta. Remember to pull out the extra 1/2, so we're going to have 27 fourths right there, and then plus 54 theta from 0 to 2 pi. And then the one over here is just going to be u minus 1/3 u cubed from -1 to 1. Alright, let's see what we get here. Plugging in 2 pi, and the one here on the left, plugging in 2 pi, 27 halves times 2 pi is going to be 27 pi. Let's see, plugging in 2 pi for sine is going to give us sine of 4 pi, so that's gone. And then plugging in 2 pi to the second one, 54 times 2 pi is, what is that, 108? And then if I plug 0 in there, I get nothing for all of that. So I get 27 pi plus 108 pi for that piece. Second one is going to give us, plugging in a 1, get 1 minus 1/3, minus plugging in -1, you get -1 plus 1/3. 1 minus 1/3 is 2/3. Subtracting a -2/3 gives you 4/3. So ultimately what we get out of this is the 4/3 from the green part. And let's see, 27 and 108 is going to be 135 pi times 4/3. And is 135 divisible by 389? Yes, it is. So let's see, that's going to be 45. 45 times 4 is 90, 180. So we're going to get 180 pi. Okay, that's the flux that we were looking for. Now, that process took quite a bit of time. That was doing it the old way. Okay, that was actually finding the surface integral over this thing. Using the divergence theorem is going to make this much, much easier and quicker. So first of all, and you see we don't have much room left. Good thing is we don't need it. Let's find the divergence. First of all, let's go ahead and separate this. You're going to see how nice this divergence theorem really is, because it's going to give us the exact same answer in that little amount of space that I have left here on this page. So the divergence, let's find the divergence. The divergence of f, remember, is, and I'll just write it real quick here, it's d dx, d dy, d dz, dotted with, in this case, our force was 3x, 2y, 0. So our divergence is the derivative, when you dot these things, it's the partial derivative of the first component with respect to x, well that's 3, plus the partial derivative of the y component with respect to y is 2, and then the last one is 0. So our divergence is 5. And according to this, we are taking the triple integral of the divergence, and we're going to do this in spherical coordinates. So let's set up our triple integral in spherical. So we're going to take the divergence of 5. We are doing it in spherical coordinates. Now we haven't parameterized anything. There's nothing to parameterize here in this case. So we're going to do it in spherical, which means we do need the extra component of the rho squared sine phi. And then we're going to do, d rho, d phi, d theta. So remember that theta, because it's a sphere, goes from 0 to 2 pi. Phi goes from 0 to pi. And rho in this case was, what was the, I think it was 3 in this case, because it was something equals 9. So it's going to go from 0 to 3 Hopefully I didn't do that wrong. I didn't scroll back up to double check that. But we can separate all of these. So let's go ahead and do that. So we're going to get integral from 0 to 2 pi. The only thing I have with theta in it is d theta, times the integral from 0 to pi of sine of phi, and the only thing that d phi, and the only thing that I have with rho in it is rho squared, 0 to 3, and I'll just put the 5 with the rho squared. We could have put the 5 anywhere, d rho. So let's go ahead and figure this out. So we're going to get the integral from 0 to 2 pi of d theta we know is just 2 pi, times the integral of sine of phi from 0 to pi. Integral of sine of phi is going to be, what's that, negative cosine? Is that right, negative cosine? Yeah, negative cosine. Just drawing a blank there for a second for some reason, from 0 to pi. And then the integral of 5p squared is 5/3, p squared, rho squared is 5/3 rho cubed from 0 to 3. So we get 2 pi. Plugging in pi for cosine is -1, but the negative negates that, so we get 1. Minus, plugging in 0 gives us 1, so it's 1 minus minus 1, which is actually plus 1. And then times, let's see what we get here. If I plug in 3, we're going to get 3 cubed, which is 27. 27 times 5/3 is 27 divided by 3, which is 9 times 5 is 45. And then plugging in 0 gives us nothing. So ultimately what we get here is, let's see, this 1 plus 1 here is 2. So 2 times 2 pi is 4 pi. 4 pi times 45 is 180 pi. Using the divergence theorem, much, much easier. We'll come back and we will prove 4 more. Again, we will do it the long way with the surface integral, and then we're going to do the divergence theorem and show you how much quicker and easier it is.